Good evening, everyone, and welcome to tonight's Cape Center meeting. It is a pleasure to welcome you all, whether you are a member or guest. And of course, it is a real pleasure to introduce tonight's speaker, Dr. Sarah White. Dr. White first enjoyed learning about radio astronomy as an undergrad at the University of Cambridge, and after that, she moved on to the University of Oxford, where she studied quasars for a PhD. And after that, her first postdoc took her to Australia, where she used the Murchison Wide Field Array. And then in 2018, she came to South Africa on a Sereo Fellowship affiliated with Rhodes University. And she is using Meerkat to continue her research into active galaxies. Sarah, thank you very much for coming tonight, and over to you.
Thank you so much for having me. I'm just going to share the slides now. And is this full screen? And the next slide, can you see?
All good.
All good, great. Yes, thank you everyone for attending also. So as Christian has nicely introduced me, my name is Sarah White and I'm a postdoctoral fellow at Rhodes University. And I am most interested in learning more about how galaxies evolve over time, and in particular, the radio emission that we get from these objects. And today's talk is going to be on the brightest galaxies that we see in the radio sky, thanks to the variety of radio telescopes across the world. But focusing on one in particular, we'll see later. So, most of you, of course, will be familiar with how the night sky looks in the optical. It's very easy to pick out stars and planets, and maybe a few galaxies, but to see more distant objects far beyond the Milky Way, we also need to make use of these very large telescopes. And so this is a time-lapse image taken at Sutherland, and in the foreground is the Southern African Large Telescope, SALT. And why optical wavelengths are so crucial is that they give us an insight into how distant those galaxies are, because through an optical spectrum, we basically get a measure of how bright the source is as a function of wavelength. And we can pick out these emission lines, which when we compare them to where we would expect the emission lines to be for a particular element in the lab frame, we can see that for the more and more distant objects, those emission lines or absorption lines get shifted further towards the red end of the spectrum, hence the name of redshift. So the more far away the object is, the higher its redshift will be. But also in the optical, we can get an idea of how much star formation is taking place in a galaxy from its overall color. So when we do have high rates of star formation, the stars tend to be more blue. And so that gives you an indication of high star formation rates. But you also have galaxies where that star formation has kind of switched off a long time ago. And therefore, the light appears to be more red from those objects. So there's different pieces of information that we can get in the optical. But one of the downsides we have to worry about is the fact that cosmic dust can get in the way. So this is most obvious, of course, when we look up at our own Milky Way and we see these beautiful dust lanes across the sky, and that's blocking some of the optical light that's being emitted. So you can imagine also if you focused on a particular galaxy at maybe high redshifts, very far away, there are some galaxies that are completely enshrouded in dust, and so we wouldn't see any optical light from them at all. And this is why if we do our selections focusing in the optical, we might actually be missing a lot of galaxies. And so this is one of the driving factors actually for using radio observations, because they are unaffected by dust along the line of sight. So to kind of illustrate that, I'm going to consider the electromagnetic spectrum, and we can see we're more familiar with the night sky in the optical, the visible part of the spectrum. But if you look over here in the radio, we've actually got a very nice window in the Earth's atmosphere over which those radio waves are able to make it all the way down to the Earth's surface where we have our telescope set up. And this is a nice wide window. Each of the numbers here, that's the wavelength, different parts of the spectrum in units of meters. And in the radio, we have multiple frequencies at which we can observe. And I'm going to actually start with low radio frequencies. And by that, we're meaning the longer wavelength radio light. And here are two key low frequency telescopes that we have. So in the Northern Hemisphere is LOFAR. That's actually based in the Netherlands, but has different stations across Europe. And that includes Sweden, hence which is where this photo on the top has been taken. And in the Southern Hemisphere, in Western Australia, we have the Murchison Wide Field Array. And this is actually located in the place where the SK Low precursor telescope, SK Low will be built, because this is the precursor telescope for that. So by observing at low frequencies, we can also get a more complete picture of the sky, especially as the radio emission from galaxies ages, it moves to lower frequencies. So not only do we get around the dust problem, we also can pick out galaxies that might have kind of switched off. There's no longer ongoing activity, but we can still pick up the remnant radio emission at those low frequencies. So to also illustrate this a bit further, I'd like to, if you've not heard of this before, this a very nice tool that's online called the Gleamoscope. If you go to this website, you can look at a patch of the sky and scroll between these different parts of the spectrum to see, well, how much does it actually change? We're more familiar, of course, in the visible. But if you scroll down, this is the same patch of sky. Now scrolling down to the radio, this data comes from an all southern sky survey called GLEAM. So that was conducted using the Murchison Wide Field Array in Western Australia. And you can see kind of flicking between the two, the difference it makes. So if we focus on this huge radio galaxy in the middle, this is Centaurus A, and we have these two extended radio lobes. See, that came from this tiny dot in the optical, and it extends about 9 degrees across. But I'd also like you to focus on this other extended source. So in the optical, we see lots of point light objects, but in the radio, we also get these quite unusual morphologies. So up here, we can see another example of a radio galaxy. We have 3 peaks in the radio emission. And my collaborators have referred to this as the TIE Fighter galaxy, reminding us of course, the Star Wars movies. But in the center, that's where the radio core is, the supermassive black hole in the host galaxy. And emanating from that to the radio jets and the 2 lobes on either side, and where that relativistic emission is interacting with the surroundings. So maybe let's spend a bit more time talking about the actual different parts of an active galactic nucleus. So that's where we have material, a gas, falling onto a supermassive black hole. And as it does so, it produces a large amount of emission over multiple wavelengths. So surrounding that supermassive black hole, we have an accretion disk forming in many cases. You can think of that as kind of a whirlpool of gas. And beyond that, we also have what's known as this dusty torus. And so you can see, because of the geometry of these objects, the angle at which you're viewing the object makes a big difference in the properties that you're going to get with your telescope. In some cases, we have these powerful radio jets being produced, as illustrated here. So of course, if you happen to be looking down the radio jet axis, then you're going to see much different properties compared to at an angle or even side on. The other thing is that if we are viewing this active galaxy side on, maybe the dust is completely obscuring the optical light from the accretion disk at the center. So this is something that we need to bear in mind when we construct our samples of these sources and when we interpret the data as well, because we may have a whole or a mixed bag basically of these sources, all at different orientations. So we have to think how that would affect our conclusions. So how do we know that we do have supermassive black holes at the center of galaxies? Well, a good starting point is to consider our own galaxy, the Milky Way. And we find through many years of monitoring of the stars very close to the supermassive black hole at the center, through their motion around this position, we can use their velocity and the radius to calculate, well, this much mass must be enclosed within that radius. And so once you have the radius and the mass, you can then calculate the density, and therefore the only thing that could explain the motion of all these stars, and some of those stars can be very dramatic, very like as this one reaching its closest approach back in May 2018. It's through those trajectories that we can establish, okay, something incredibly dense is here, and the only explanation we have for that is that there is a supermassive black hole present. And I'd like to spend a bit more time on what is meant by the accretion disk. So some of you may be familiar with this image. Many scientists were involved in advising for the movie Interstellar. So this is part of the same kind of simulations that were done and also became publishable work. So it wasn't just doing the graphics for a movie, they were also learning more about something called ray tracing, the accretion disk. So as mentioned before, I described this as kind of a whirlpool of gas surrounding supermassive black hole. And a reminder that nothing can escape from the supermassive black hole. Anything that crosses what's known as the event horizon will not be able to leave again. And that includes, of course, photons of light. So when we talk about later these radio jets emanating from these objects, it's not actually coming out of the supermassive black hole, it's coming more from kind of a spherical surface of relativistic plasma. So the reason why do we get this odd shape along the top? Well, this is because the way in which that supermassive black hole is actually distorting space-time itself. And so this hump basically at the back is, that's us being able to see the far side of the accretion disk, which of course is in a single plane. And in this case, beneath, this is actually the image of the underside of the disk. That's how much the light is being bent by the supermassive black hole there. And so what are radio jets exactly, and how do they form? Well, that's a very good question, if I do say so myself. The truth is we are still not sure. There are limitations in both the observations and the simulations as to how exactly are these powerful radio jets being launched. So we're kind of pulling together different pieces of the puzzle, but haven't quite got there yet. But the idea is that kind of connected also to this accretion disk, remember that we have to also think about magnetic fields. And those magnetic fields can get kind of twisted up by this motion, the accretion disk. And this can lead to a kind of a funnel being created where these magnetic field lines are then twisted up and almost directing the relativistic plasma alongside within the jet and out away from the accretion disk. And so that would actually usually emanate in both directions, bipolar outflow. So yes, still lots to learn about these objects. And just to spend a bit more time on the radio jet itself, a reminder that when we're studying the light from these objects, we have the electromagnetic waves, they're oscillating in different directions, but if they undergo some kind of mechanism, they interact with maybe a common medium, then that light might become what's called polarized. And in the bottom left, we have what's called Stokes parameters. So these are ways to kind of quantify, to measure how much polarization we have. Either is the light horizontally polarized, do we detect it vertically or at an angle, or do we have circular polarization? And in the top right is an example of magnetic field lines for a radio jet. Each of the white lines, the direction of the line gives you an idea of the direction of the magnetic field. And it's only within the jet that you can see it becomes more disordered. So it's very ordered along the surface of the cone, but inside it, it's a lot more turbulence, and hence this kind of structure like so. So yes, I mentioned that these Stokes parameters, and if there are any cricket fans in the audience, hopefully you recognize this guy. Now, how do those radio jets actually interact with their surroundings? So this is a great composite image put together by Francesco de Gasperin. And each of these images have been taken at different radio frequencies. At low frequencies, that's how we really get a full impression of the large spatial scales over which these radio jets can have an influence. And so we can only detect this very diffuse emission if we have sensitive enough telescopes, but also it's much easier to detect that kind of emission at low frequencies. Now, by going to higher frequencies, we can kind of zoom in on specific regions. So that's what this image here is taken from kind of the mid center of this low frequency image. But this is using the Very Large Array, which is in America. And with this higher frequency, we also get better angular resolution, which allows us to more clearly see the structure within the jets. And then we can zoom in further still by using what's known as very long baseline interferometry. So this is where we have the antennas of a radio telescope being sometimes hundreds of kilometers apart. And that kind of separation allows you to get the resolution needed. But the downside is that you then tend to become more limited to the brightest radio sources. Some of those fainter sources, that amount of that intensity would kind of get washed out in a way. And then finally, for this source M87, of course, hopefully you've seen this amazing groundbreaking image that we got from the Event Horizon telescope. So this is the first ever imaging of a black hole's shadow. So we're not actually seeing the black hole itself, of course, because no light can escape from a black hole, but we can see the shadow it's casting, and around it, the accretion disk. So that's all very exciting. And I believe they're following up some other nearby supermassive black holes to look out for those in the news too. So now we get onto my favorite part, which is talking about the Meerkat telescope. And genuinely, this best radio telescope in the world. It's located in the Karoo Desert, and it gets its name because originally there was the Karoo Array telescope, and decided it worked so well, we want some more of that. So we have Meerkat, which is composed of 64 dishes, and each of those dishes is 13 meters across. And the image that we're getting from this instrument are just amazing. The sensitivity is far beyond the design specifications. So actually, some of the original surveys that were conducted using this telescope almost had to be adjusted because it was performing beyond expectation. So that's awesome. And one of those amazing images we've obtained with Meerkat was of Fornax A, one of the brightest radio galaxies in the sky. So the meerkat image is in red, and this is overlaid on an optical image, so you can see the host galaxy at the center. And what's so stunning with this image is that you can really pick out that filamentary structure within the two radio lobes. So those jets would have interacted with the surroundings, and you get this lovely kind of woofly, fluffy, kind of cloud-like radio lobes. And it's just, yeah, quite amazing to look at, because radio astronomers have become almost used to looking at radio images that are very blobby, quite low resolution, but now we're getting these amazing images because of the combination of sensitivity and also angular resolution. So really a level of quality that is starting, matching some of the optical images that we may be more familiar with. And of course, no radio galaxy talk would be complete without a nod towards Bernie Fanaroff and Julia Riley, who came up with the key morphological classification back in 1974 that we've been using ever since. Of course, many of you will know Bernie Fanaroff as a giant in radio astronomy in South Africa, and it's really awesome that we've been able to get this great telescope here. And looking more recently, he's published this wonderful piece of work revisiting some of those old radio galaxies that had been observed back in like the 60s and 70s, but seeing, well, what do we see now with Meerkat and UGMRT, which is a telescope in India. So just to explain what exactly was the morphology classification they came up with. Well, for these radio galaxies, basically split into two categories. One the top being FR1. So this is where the radio emission is brightest in the center. Hence, you can see the density of the red contours is a bit more dense at the center. And then it kind of fizzles out towards the edges as the radio emission kind of dies away. Whereas in the FR2 galaxies, instead of being core brightened, these are now what's termed an edge brightened. So the brightest radio emission is actually at the extremities, and that's where the jets are really plowing into the surrounding medium and energizing that region. And in many cases, you also get the creation of what's called hotspots. So those are a good indicator that, okay, we have an FR2 galaxy here. It becomes a bit more difficult sometimes to decide to differentiate between different morphologies if your resolution isn't good enough. So, but thankfully we don't have that problem with Meerkat. So now to just spend a bit of time on, well, how does all of this fit in general? Let's provide some context for our studies. So, of course, soon after the Big Bang, the universe underwent some rapid inflation, and then we have this, what's known as the epoch of recombination and reionization. But where the region that we're kind of more interested in for galaxy evolution is kind of, the more recent when we look at the history of the universe. The first stars and galaxies being formed just over 1 billion years ago, and you can see that we've gone from kind of this kind of soupy kind of plasma. Over time, you might have some perturbations, some slight overdensities. When you get those overdensities, that's what's then causing a greater gravitational attraction, which then pulls more gas together, and that's how those first stars and galaxies are forming. So there's this kind of coagulation, this cosmic web being formed with all these lovely filaments. And also, if you've got many galaxies coming together, then you form what are known as galaxy clusters. So imagine you're looking at this the structure, and you take just a slice through here, you'd get something that looks like this. So again, this coming together of the merging of galaxies. And in this cluster, we also start to encounter some problems actually where we can't quite explain the observations. At first, there was the question, well, why, given how much gas is kind of streaming in along these filaments and concentrating at these nodes, why don't we get as much gas at the center as we would expect there to be? And that's where we bring in the idea of feedback from the active galaxies, the ones producing these powerful jets, because as those jets propagate outwards, they can either, they're pushing the surrounding medium aside, but they can also, depending on the density, the relative density of the jets compared to the medium, they can inflate these bubbles basically either side of the supermassive black hole. So in this particular image, we've got the radio emission indicated by these white contours, and that's overlaid on a background image in the X-ray. So we have the brightest X-ray emission shown in yellow here and here, but the darker blue is kind of our indication, okay, we've got this cavity being created because of those jets kind of blowing holes in the surrounding medium. So that's one way in which the jets interact with the surroundings. But of course, it can go two ways as well, because the more turbulence there is, then the more likely it is for some of the surrounding medium to become what's known as entrenched within the jet. So a jet that might have started off going very fast, then starts to slow down as it gains more mass and more momentum. Now, some of these radio galaxies have very strange shapes. They're not all, they don't all have radio jets in exactly opposite directions. And that's because some of them may also be moving relative to their surroundings. And that's what's happening, for example, in this object moving through the Perseus cluster. So those two jets, which were originally being ejected in opposite directions, they've both become like bent backwards because of that relative motion. Now, and this is where the observations can also lead to different morphology classifications. Because if we were to consider, for example, on the left, this is a low frequency image, we can see this whole trail of radio emission, and we can pick out, well, this seems to be a narrow angle between those two jets and the lobes they've formed. So maybe we would label it as a narrow angled radio galaxy, narrow angled tailed radio galaxy. But if our data was actually more limited, then maybe we would only see this region closer to the supermassive black hole, so it's the radio core here. And in that case, we would probably label this as a wide angle tail radio galaxy. So this is just to highlight that some of these morphologies can change based on the frequency you're observing it, and the sensitivity, maybe also the resolution. So there's quite a few things to consider, but ultimately, well, we want to know how do these objects contribute to maybe the star formation in the host galaxy, and what can they be used as probes for the surrounding medium? So you can imagine a denser medium might have a greater impact on the bending of those radio jets, whereas a less dense medium would leave it largely unaffected. Now, another thing we find in the radio sky are some very unusual sources known as X-shaped radio galaxies. And I like this one in particular. I refer to this as the butterfly radio galaxy. And here we have the low frequency emission is represented by the red contours. So that's the closest frequency in this case to the meerkat frequency, that's in blue. And this is all overlaid on a mid-infrared image from WISE. And it's inverted so that each of these black dots are representing hot dust of galaxies, but you also have some stars. So those are where you've got this diffraction pattern, the cross hairs almost like that. But we're most interested, of course, in the host galaxy at the center of this X-shaped source. So how on earth do we get X-shaped radio galaxies in the sky? Well, it is possible that there's actually two supermassive black holes that are present, but it's just that our resolution doesn't allow us to distinguish them. So in the case of this object, 3C75, we can see there are actually two radio cores there, and each supermassive black hole has its own set of radio jets. So those become superimposed. So it's possible that maybe we have a similar superposition that gives you the radio jets in one direction and then another set of radio jets in a different direction. So that's one explanation for these X-shaped sources. But with Meerkat, which is just amazing, we get this stunning image. This is 10 hours observing with Meerkat, and you can see this beautiful filamentary structure within the lobes and how those filaments kind of curve round close to the host galaxy. Now, if we did have two sets of radio jets superimposed on one another, then we wouldn't expect to see such structure. And so this is how we can invoke the alternative explanation, which is that we have a hydrodynamical model. And that's where you have the radio jets kind of switching on in this approximately north-south direction. It switches on, energizes that surrounding plasma, which then falls back towards the center again, as illustrated in the bottom right. But as it, just due to gravity, this local potential well, as it sinks back towards the host galaxy at the center, it then encounters a dense reservoir of gas. And so you can imagine this plasma, which is nicely energized, is also going to be more buoyant, it's lighter, and so it's kind of almost going to float or get deflected off the denser material that's already at the center. So that's how you can go from this structure in approximately north-south direction, and then as it falls back towards the center, it then gets deflected, giving you this approximately east-west direction, which is really nice. What's also pretty impressive with this image is that you can hopefully see a distinction. It's almost like a sheath across the north-south direction, also referred to as a cocoon. And what's nice here is that over time, the emission there has been able to equilibrate. And so you can use the brightness of that emission in this region to make an assessment of how much pressure there is in the surrounding environment. So it's almost like a barometer in a way. So that's also really neat to see, because with previous telescopes, you wouldn't see such a distinction. But of course, that comes with observing for a large amount of time, but also doing your calibration and imaging of the data really carefully, so that you can pick up this really faint emission, even when it's nearby some very bright emission. So that's why the dynamic range is really crucial. Another of my favorite radio galaxies is also belonging from the Gleam-Florjansky sample. So that's the sample of the brightest radio galaxies in the southern sky, who have this lovely Z-shaped radio galaxy. And you can see how in the Meerkat contours, which are in purple, you get this nice kind of wobbling effect. And how does that come about? Well, a possible explanation is that we actually have the radio jet axis precessing. So imagine a spinning top. You've got the radio jets, emanating in opposite directions. But if there is something that is causing the supermassive black hole to kind of wiggle and move around and spin, maybe there's another massive body nearby that's perturbing it and creating this torque. then you'll get this radio jet axis processing as well, and kind of carving out this nice helical corkscrew structure, as illustrated in the bottom right. Now, this image in the bottom right is actually of an X-ray binary or a microquasar called SS433. And being an X-ray binary, we detect these in our own galaxy. So these are stellar mass black holes, and we get this very nice kind of corkscrew structure. This image has come from the Very Large Array, again, the one in America. But what's pretty cool is that this is a stellar mass black hole, and we're seeing the same kind of structure even in these supermassive black holes are much further away. So that's pretty nice in terms of, well, maybe we have the same physics going on, it's just at much, much larger scales. So if you're also more interested in this, please let me know. I can send you a couple of papers to look at, and also looking forward to my master's student, Kateo Sejake, publishing this work this year. And then when you think you've seen everything, MeerKAT gives you this awesome image of an extended radio galaxy. Again, you can pick out these individual kind of filamentary structures within the lobes, how those jets have propagated through the surrounding medium. But the most interesting part are these collimated synchrotron threads. So we've had never seen these before. They're very bizarre. Haven't fully established how they're created. An idea is that they're actually kind of magnetic flux tubes. So maybe they may already exist, but are not detectable until they've been kind of ignited by a relativistic electron, maybe escaping from the radio lobes. So those are very cool. And just to also note that the slight bending of these radio lobes in this direction is due to this host galaxy moving towards the center of the cluster, which is towards the north in this direction. So that's, again, as I was saying before, that can lead to a distortion of the radio lobes. So we have never seen these threads before, and the reason we can detect them, as mentioned, is by doing very careful calibration and imaging the data and getting high dynamic range. Otherwise, they would basically kind of be saturated by the very bright emission you get closer to the supermassive black hole and the brightest parts of the radio jets. So if it was a limitation in our telescope or imagings before, that meant we couldn't see these threads, then just how common are they? Is this a one-off case, or do we see them for many bright radio galaxies? Well, it just so happens that, yes, we do see some threads again. And this is a source from the Gleam-4-Jansky sample, IC4296, an example of a restarted radio galaxy. And I'll come back to how we can tell it's restarted in a moment. But close to the host galaxy, which is here, we see again, it was really exciting to see, wow, those threads that we discovered before, this work by Patti Ramatsoku. So again, we see these threads quite close to the host galaxy. But what's interesting is that they appear to be linked to the instabilities within the radio jet itself. So if you, go to this paper and look very carefully at the radio emission within this northern radio jet, then you'll see this kind of wiggling effect, this instability, and right at the point where it's kind of hitting the surface of the outflow, you're getting some of those relativistic electrons are then able to escape, and they kind of feed and ignite these threads close to the host galaxy. So that's why that's what's referred to as the threads in the title of the paper. But we also have what are known as ribbons, and those are that's really referring to this the straight parts of the radio emission. Why that's so unusual is, well, it's as if those radio jets have switched on, carved out a tunnel through the surrounding medium, switched off. The plasma in those tunnels start to reach equilibrium and even out. And so that's why you get very, very uniform radio brightness here. And so again, if you know the volume there, you can then work out, well, if it's reached this brightness, it must be at this temperature, it's over this volume, so maybe we have this amount of pressure in this region. So having switched off these tunnels, these ribbons reach equilibrium, but we then see, oh, well, there's a lot brighter radio emission near the center again, so it looks like the radio jets have switched on one more time. So this is why we refer to it as a restarted radio galaxy. So remember that these radio jets are not continuous, they can go through these life cycles. And then finally for this image, the rings, that's referring to this southern radio lobe. It's not quite clear in this image, which actually comes from the press release, but if you go to the paper, then, and I can point you towards that if you're interested in it, in the southern lobe, we see the filamentary structure is such that you actually get these elliptical kind of shapes, like one on top of the other, or concentric in a way. And from the geometry of those ellipses, you can then calculate, well, this must be the angle at which that radio jet is going, what direction it's going. And that's important because remember, of course, all of our images are 2D projections of 3D objects. So what we really also want to know is, okay, how is the brightness of the object also being affected by its angle with respect to the line of sight? So this is now a novel method, another way of calculating, well, this radio jet, yes, it's in this direction, but how much of it is actually inclined towards us? So just a huge wealth, a huge amount of information that we're getting from this single meerkat image, which is pretty incredible. So why do we care about the radio jets again? Well, in some cases, they may impact on this otherwise stable molecular cloud, triggering its collapse and subsequent star formation. So that's the radio jet indicated by the contours here. And the grayscale is the molecular gas, not molecular, sorry, H1 gas, as that's an indicator of stars forming. But in other cases, you can get the radio jets doing the complete opposite and preventing stars from forming. And there are two kind of main mechanisms for that. One is a radiative feedback. So that's where it's more to do with the accretion disk, but also the jet can push out the gas, push it far enough away that the density then becomes too low and can no longer collapse to form stars. And another mechanism is this kinetic pathway. So in this case, those relativistic jets are kind of pumping thermal energy into the surrounding medium, and that heat then prevents stars from forming as well, because the two kind of main criteria that you have to have the right density and you have to have the right cool temperature in order for stars to form. And so this is bringing us to the final slide, where the fact that we really need to build up a multi-wavelength picture in order to understand all the different mechanisms in these objects, active galaxies, but in all galaxies really, in order to better understand how they evolve over cosmic time. So in addition to getting the redshift, of course, from optical spectrum, optical emission also tells us about the accretion disk surrounding that supermassive black hole, and any ionized gas that's also orbiting at different distances, different radii from the supermassive black hole. In the mid-infrared, that's a good way of picking up that the warm dust or hot dust in these objects. In the X-ray, that tells us more about the hot gas that's being excited. And in the radio, we pick out the core, the accretion disk again, connected to surrounding the supermassive black hole, but also how it's interacted with the surrounding mediums and surrounding medium and created these two radio lobes. So this is what radio astronomers may call a continuum. So by that, we're kind of collapsing all of our information in the frequency axis, combining it all together and saying, right, okay, what is the intensity of the radio emission at these positions? Whereas you can also take what's known as spectral line observations using radio telescopes. And that's quite similar to the optical spectrum I showed at the start. Basically a function of, the radio brightness as a function of frequency. And from that, you can, if you know what wavelength you expect a particular element to appear at, but you also get shifts to that. In addition to the redshift, you get a shift on that based on the motion of the gas. So if you do have this gas orbiting in a disk, then the gas that's slightly coming towards you will be slightly blue shifted, and the gas that's moving slightly away from you will be slightly red shifted. So those are extra pieces of information we want to understand. How do those radio jets impact on the surroundings? What is the relative motion, but also do they actually prevent stars from forming or not? Because that's it's black hole accretion, gas falling onto the supermassive black holes, and also the growth of galaxies through star formation that gives us our different galaxy populations over cosmic time. So I'm now ready for questions, and if you are a little stuck, then I've also left up a slide here. So please feel free to pick one of these, or I'm happy to hear from you. Thank you.
Thank you very much, Sarah, for that great presentation. And yes, the floor is open for any questions.
If black holes swallow up everything in their domain, does that mean that eventually everything is going to be inside black holes, the whole universe? I'm not talking about tomorrow, but I mean far, far ahead. In which case, would there be a possibility of a black hole disintegrating and making another Big Bang?
So there's actually a common misconception about how material actually gets into the black hole. So it doesn't do any sucking at all. Material doesn't get sucked in. It's more to do with the trajectory. If it happens to be losing angular momentum at the right rate, then it will fall into the black hole. So there's not really a danger of the entire universe collapsing into these black holes. What we're still seeing evidence is that the universe is still expanding, but at a much slower rate. And so the crucial bit will become, well, if it starts to slow down to such a point, then maybe the gravitation of all these galaxies will start to pull it together again, and you'd get a big crunch. So that's kind of a more likely scenario than everything getting sucked into black holes.
I see no hand up, so let me ask a question, Sarah. I think that is about slide 27, about the X-shaped galaxies. If I understood you correctly, you've basically outflow material which comes back falling in, and then is deflected by the dense inner material. But why is it deflected asymmetrically?
So that was determined through a bit of modeling, basically. So it's largely down to the geometry because of the angle with respect to our line of sight. If it was a bit more, I guess, perpendicular to the radio jet axis, then maybe it would have taken on a different shape. But this is, through the models really of the geometry, it's, looks like so in the bottom right. But it could have I've not seen cases where it's kind of fallen down and then it could have, I guess, gone in both directions. It could have deflected, but yeah, I think that that would, yeah, depend on the relative angle to our line of sight as well.
Thanks.
I saw Ketchell's hand up first, I think.
Yeah, okay, so in one of the graphs earlier, it said the legend at the bottom, it said relative RA, and then at the side, relative dec.
Where was that?
Relative to what?
Oh, this one.
Yeah, relative
right.
RA and relative dec. Sorry, I don't know what they mean.
Oh, I think it was just that they'd already specified maybe the RA dec somewhere else in the paper. And this is to give you an idea of, well, what is the angular size of this image? Okay. So in this case, it's 100 arc seconds across. Mm-hmm. Yeah, so yeah, they would have quoted, yeah, the original position somewhere.
Oh, okay, I just thought I was really missing something very basic I ought to know about.
No, that's good. I think, yeah, just for ease, they centered it on 0, 0. Yeah.
Richard, your hand is up.
Oh, thanks. That was most interesting. Tell me, the question is, when you're doing the calculations for a star around an unseen object, do you need to know the distance? And more specifically, do you need to know the distance between the object and between the star and the unseen object? And if so, how accurately?
Could you repeat that? Sorry, I was just getting to the slide.
Okay, when you're doing the calculations for the orbit of a star around an unseen object, do you need to know the distance away? And more specifically, do you need to know the distance between the star and the unseen object?
Well, that's so that comes down to the trajectory that's been monitored over several years. So you have these stars moving in different directions, and they're kind of, it's almost like a catapult. You know, if the star comes very close to this point, then it'll, you know, move around and you get this closest approach and then gets shot off again. So with stars moving in different directions, you can start to kind of triangulate where that unseen object actually is. And so from that, then yes, you can calculate. So the point of closest approach is the most useful. But in the end, you have these objects following Kepler's laws. And so you can use those equations to work out, okay, the velocities, and therefore how much mass must be acting on those bodies in order to get that kind of slingshot motion. I hope that
answers. Thanks. And what is the typical closest approach?
Well, this one is saying for S2 is 20 billion kilometers. So 120 times the distance between Earth and the Sun.
I see. Fine. Thank you.
Yeah, no worries.
Ketchell, your hand is up again.
Yeah, so this isn't really a question. It's just that I've watched too much sci-fi. So I always want to know, if you were on a planet orbiting one of these stars that's getting close to a black hole, you know, what would it look like? I mean, I guess that the star would be moving more quickly relative to the background stars. You know, you will be aware, if you had instruments, I suppose, you will be aware of some sort of movement around the black hole as you're sort of catapulted out. But you know, what would you see in the night sky?
For a star near a black hole.
If you're on a planet orbiting a star that's relatively close to one of these black holes, but it's not going to fall in. It's going to be catapulted out. But what you might see in the night sky, or I'm always intrigued by what it would be like to see two suns and all those, just what it would look like.
Well, I'm not sure, to be honest. I would be. For me, the bigger concern would be I wouldn't want to be that close to a supermassive black hole at all. That was my yeah. I'm not sure because also think about how much radiation, if there is ongoing accretion activity across this black hole, around this black hole, then that's producing a huge amount of radiation. And so maybe we don't need to worry about what it would look like, because if there are any planets, everything would be destroyed by the radiation. So, yeah, it would be very difficult to survive in those extreme conditions.
Oh, they said that, didn't they, about the bottom of the ocean?
No, true. True, and there's still life down there. Yeah, we actually, isn't it, we know more about the surface of the moon than we do about the bottom of the oceans on Earth. So, yeah, lots to learn.
Mm.
Indeed. I see no hand up. Does anyone? Oh, there is a hand. Richard.
Oh, yes, me again. You mentioned earlier when you were using a telescope in an interferometry mode in order to get more resolution, you were limited to only the bright stars. Are you saying that when you use it in that mode, you get less sensitivity?
It's not, first of all, not bright stars, but we're looking at very bright galaxies. So yes, for all radio telescopes, you've got this, you have to reach a compromise of, are you optimizing for resolution or are you optimizing for sensitivity? And what's great with Meerkat is that we get kind of the best of both worlds simultaneously. But with very long baseline interferometers, you're really geared more towards the resolution side. And so you have to sacrifice some of the sensitivity. Maybe if you had many more of these dishes with similar baseline, similar separations of the antennas of the dishes, then you would be able to build up that sensitivity. But it is kind of a numbers game in that case. Your Meerkat has 64 dishes, and some of the email and I believe only has 7 dishes. So yeah, there's that trade-off. In terms of paying for the infrastructure, how do you distribute your dishes? Do you want to go more for the sensitivity or resolution? So yeah, a lot of the very long baseline interferometry work kind of focuses on, okay, if they're the brighter emission and brighter objects to start with, then we're going to lose less flux if we then observe them with this instrument anyway. And so that's also how some of those studies can then become biased. You know, they're favoring those brighter objects in the first place. And so what conclusions you reach might be true for that subset, but it then makes it harder to extend it to the much wider population.
I see. Okay, but why is the sensitivity reduced if you're using more dishes?
No, I didn't say that it was reduced. No, the sensitivity goes with the number of dishes. The issue is that some of these very long baseline interferometers, they don't have many dishes in the first place. They don't have the numbers.
Oh, I see. Okay, fine, thanks.
It's not just the number of dishes, it's the collecting area, right? So, you can choose, do you want to pay for fewer really big dishes, or do you want to pay for more smaller dishes? There's the construction costs as well as the distribution of the dishes. So the layout gives you, the layout gives you the resolution, but the collecting area gives you the sensitivity.
William, your hand is up.
If these radio lobes come out of the galaxy perpendicular to our point of view, why do we see it? What makes that we see it? Is it reflecting? Do we see it at the same frequency as it comes out of the galaxy? What is the mechanism that allows us to see those radio?
All right. So this is where so those relativistic electrons, when they propagate through magnetic fields, they undergo this kind of helical motion. So if you are familiar with synchrotron radiation, it's similar to cyclotron radiation. So as it's propagating, that's how we get radio emission being produced. So if we didn't have magnetic fields at all, which would be weird, but this allows, it's even low level magnetic, well, very weak magnetic fields, you'll get radio emission. So you have different types of radio emission because it could also be from the accretion disk, so it's still interacting with magnetic fields within the accretion disk. You also get it from stars forming. So the connection to radio emission from star formation is actually a bit of a delay. There's a time lag because the radio emission doesn't come from the star itself, it actually comes from the supernova remnant that's left over. So once a star has reached the end of its life and it's exploded in the supernova, it's the supernova remnant that gives you the radio emission. And so you've got, you need to factor that in as well when you're interpreting the data, that you have different timescales of the radio emission being produced. And there are other mechanisms where you've got like cluster relics being produced as well. So that's where maybe you have two clusters have merged and you create a shock front. And across that shock front, if you have electrons being accelerated or also decelerated, then you'll get radio emission being produced there as well. So there's actually many different mechanisms that can produce radio emission, and that's why we need to make use of other wavelengths as well to try and disentangle how much radio emission is from this mechanism and how much is from this other mechanism. So yeah, there's quite a lot to decipher.
Thank you.
I see no hand up, so it seems that all questions have been answered. Thanks a lot, Sarah, for that brilliant talk. Enjoy the rest of your evening and goodbye.